20 minutes in a stream. Finally got the stuff plugged in. It's fine. Okay. So Cramer's rule, you say? Okay. So as a refresher here, you got a1x plus b1y is equal to c1, and a2x plus b2y is equal to c2 is our system of equations. Okay. Then, right, if we got this, then x equals, got a determinant, c1, b1, c2, b2, over determinant, a1, b1, a2, b2. And y is equal to determinant, a1, c1, a2, c2, over determinant a1, b1, a2, b2. Okay. So alternatively, right, we've got this as a linear algebra system. a1, b1, a2, b2. Augmented. Let's not augment first. Let's just show it as vector multiplication. So here times xy is going to be equal to c1, c2. Alright, so augmented a1, b1, a2, b2, augmented with c1, c2. Alright, so if we're trying to find a solution here, we're trying to get x and y, this is going to make us say, okay, we want this to be, instead of a1, b1, b2, a2, b2, wow. We're going to say, alright, we want this to be 1, 0, 0, 1, to be an identity matrix. So in order to do that, we're going to have to multiply our top equation by a2 and our bottom equation by a1. This will allow us to get rid of our x's, and then later we can reverse it and go for y's, or we can just start from do I want to go that way? That'll be fine. Alright, so clear out the first column. It's the easiest way to go. Yeah, right. It's been a while since I've done this in general. Most of the time I'm using actual numbers, so it's a little easier to follow with numbers. Alright, so here we've got a1, a2, b1, a2, augmented with a2, c1, whatever, that's fine. a1, a2. This needs to have opposite signs somewhere, so arbitrarily assigning it to the bottom, because that's just what you always do. Right, we want the top to be, to have our positive value in the first position. Alright, so this is B2A1, negative. And then this is going to be negative A1C2. So we're going to add row 1 to that. So we get A1. We can go back here. Let's do this as we're also going to multiply this row by 1 over A1, A2. So here we get a 1. Here we get a B1, A2 over A1, A2. So those are your A2's gone from that term. With A2C1 over A1, A2, which again, A2's are gone from that. Then down here we get a 0. Down here we get a, none of those are the same, so that's alright. So this is going to be a B1A2 minus B2A1. And down here we get, again, same, none of the same, A2C1 minus A1C2. Alright, we need this term to go away, which is currently a B1 over A1. So we need to add this stuff to that stuff. This needs a common denominator. So we're going to get A1 there. This is going to be A1, B1, A2 minus B2, A1 squared. Ugh. Some of this stuff is going to clean up. Bold claim. Right, or we could divide both sides. I guess we could just divide both sides. Right, do it as the whole equation rather than... Alright. So this is also going to be multiplied by 1 over A1. It's fine. This being said, you probably wouldn't want to do all these steps at once. Spread them out. Alright, so then we can just add, that's just not gonna, okay, hang on. What else needs to be done? You know what? Back it up. Alright, let's try this again. It's gonna be painful. Oh. Good enough. Okay. This is B1A2. This is A2C1. Okay. So let's make it A1A2 on both of these. So A1A2, A1A2. Alright. Slightly better. Maybe not. Man, what did I do? Alright, so in theory, multiply the entire denominator by something really gross. I mean, we're going to have to multiply the lower equation by something gross. So it's going to have to be this thing, the thing we want, divided by this thing, the thing we're trying... Nope, other way around. This thing, the thing we want, divided by this thing, the thing we don't want. So... let's say we want just B1A2 to be there. We don't want... I'm going to regret this. B1A2 minus B2A1. Yeah, okay. So this is going to end up just with B1A2, not this other stuff. And then this thing, still pointing with my mouse, with my cursor here, you can't see it. Right? Can't see it? No, can't see it. It's so terrible. Alright, you can see it with my mouse. So, yeah, we can get this to just be that thing. But then this thing is going to be now multiplied by that. That's going to be significantly grosser, but wait for it. Okay, this needs one of those. B1A2 minus B2A1. I probably should just leave the A's out of it until the end. B1A2 over B1A2 minus B2A1. Okay. So now we've got 1, B1A2 And now we can't add it to that thing because the bottom of that's going to be messed up. Oh, no. That went away in that term. Right, that was the whole point. We were exchanging the top thing. Over here, we get the full thing. Over here, we get the full thing. Over in this fraction, we got rid of what used to be here, which was the b1a2 minus b2a1. So that's gone out of the numerator. And then this is now in the numerator, b1a2. That's it. Okay. So if we add... If we subtract row 2 and put it in here, we're going to subtract row 2. This is the exact same thing, so that's now 0. This is a 0. This is a b1a2 over a1a2. Augmented with. All right, we subtracted this denominator. So these two things here are going to switch places. So we're going to get a1c2 minus a2c1. Seems more promising. Subtract it, so up top. All right, so we get an a2c1 times, we've got to have this, this thing in the denominator as well. So it's got to be multiplied to the top and bottom of this one if we want to add these together. So b1a2 minus b2a1. All right, times a2c1 divided by a1a2 times the quantity b1a2 minus b2a1. Okay, and then we're subtracting all of this stuff. Just going to end up with plus a1c2 minus a2c1 multiplied by b1a2 divided by parentheses b1a2 minus b2a1 times a1a2. All right. Denominators, or the second row stays the same. At least for this step. All right, a2c1 minus a1c2 times b1a2 divided by all the things. Okay, we're getting there. Nothing if not persistent. Oh, great coffee. Alright, this is 1, 0, augmented with. Now, these things need to combine. This is going to be a little nuts, but it's alright. So here, what we've got is b1a2 minus b2a1 is the determinant of b1, b2, a1, a2. Or it's the negative determinant of the thing I actually want to put up here. Alright. So it's A's and B's, like this. But B1, A2 should be negative, so this whole thing is going to be the opposite of what we were kind of expecting. Okay, multiply by A2, C1. Divided by A1, A2, multiplied by the determinant of, this is A's and B's, and again, oh, wait. Right, so those things need to combine. Arg. Try again. Alright, these things need to combine. Let's do that algebraically first. Makes way more sense going this way. Okay, so here we're going to get A2 squared B1 C1. Ugh. Let's trust the process. Minus A1 A2 B2 C1 plus A1 A2. That's looking better. B1 C2. Okay, I got it now. Minus A2 squared B1 C1. And oh, would you look at that? Those things are the same. So they're going to combine to a 0. These things here have A1, A2 as a common factor, so it can be factored out. That's going to be nice. Okay. Divided by A1, A2 A1, B2 minus A2, B1, but this is going to be negative. Okay, because we switched the signs from up above here. Okay, that'll be useful in a minute. This is 0. This we can multiply by A1, A2 over B1, A2. Sorry, I lost my window for a minute there. Okay. Yeah, second window is also giving me some nice light here, so... Sure hope your homework wasn't prove Cramer's rule, because we're totally doing this. Alright, so A1, A2 would divide out from here, and then B1, A2 would also divide out from here. So we've got both of these terms in this fraction here. So those can just go away, which means what we're left with is a fraction. Let's see, A1, C2. parentheses, this is going to be negative because, again, signs are getting reversed. So positive A1C2 minus A2C1. And then here we've got the B's. So again, negative parentheses A1B2 minus A2B1. Okay, that means that these are going to go away. So now we get 1001. Solution matrix is going to be here. Again, A1, A2 is factored out. A1, A2 here is going to go away. We get a negative in the bottom. Arc. Shift over a little bit. Negative A1, A2 times quantity. Oops, where do we go? At the bottom is A1B2 minus A2B1. On the top, we've got B's first. So B1C2 minus B2C1. Yeah, that's how they do it. Okay. So the Cramer's rule that we wrote down from Wikipedia, but nonetheless, reversed B's and C's so that the negative would come out. But we can leave it as is because either one works. So here we've got now -1 in total. Multiply by all this stuff. And then at the bottom, we've got A1C2 minus A2C1 divided by A1B2 minus A2B1. Okay, 1001. Augmented with. Here we have a negative determinant of vectors B1, B2, C1, C2. Again, B1, C2 minus B2, C1. Okay, divided by determinant. Man, we're going way over here. Determinant of here we've got A1, A2, B1, B2. All right, and in the denominator we've got the determinant of A1, A2 with C1, C2 divided by determinant vectors A1, A2, B1, B2. All right, so there's Cramer's rule. All right, what'd you think? Yeah, it's the kind of stuff we don't really have time for. Now, I think in my Honors Algebra 2 class, we were actually told to prove this. And it wasn't like, you know, here's homework, go prove it. It was just, you should go prove it because if you can, you're going to convince yourself that this is true, and you're going to be able to play with these numbers, and you're going to remember it later. So I remember doing this in high school. But you know, it's been 20 plus years since I really looked at that proof. And of course, in high school, I did not do it this way either. We didn't do linear algebra. Ours was, I mean, just pretty much systems of equations, going through and solving each equation manually. So we did have, you know, a lot of what's going on the right-hand side was all the same. It was just in a expanded format. You know, we plug something in for X, plug something in for Y, and eventually come out with that. Pretty sure I would have done substitution method on it. I didn't really like the elimination method until much later. Alright. If anybody's got anything else, let me know. Other than that, we've got a few different... got some math games. We can run into Sunil's book here, see if he's got anything for us tonight. Sure, go for it. Yeah, go for it. Let me know if any part of that is not what you intended, just in case. Yep, n is a constant for this particular thing. So therefore n is going to be multiplied by your summation. K goes from 0 to log base 2 of n of 1 over 2 to the k. Yep. This mess? What do you mean, this mess? Though I will say I know exactly what this is. Alright. So, 1 over 2 to the k is equal to 1 times 1/2 to the k, which is a geometric series. Well, geometric sequence. And so the partial sum at any particular n value, so going out as far as you're going to go, however many terms that's going to be, is going to be equal to a sub 1 times 1 minus r to the n over 1 minus r. I suspect it's more or less what I have here. Or at the very least, like, yeah. So let's see. N in this case is going to be log base 2 of n. Alright, so let's just do this. So S sub 1 is going to be, A sub 1 is going to be, if we plug in 0, so I guess A sub 0 technically, but whatever, it's fine. K equals 0 is going to make this 1, so that's just 1. Second partial sum is going to be 1 plus, next number is a half, which is going to be 3 halves. Right, S3 is going to be 1 plus a half plus a quarter, which is going to be, right, 3 halves, 6, 7 fourths. S sub 4 is going to be 1, a half, a fourth, and an eighth. This is 14, it's going to be 15 eighths. r is a half. It's the thing you're multiplying by over and over again. Your a sub 0, like I said, in this case, is going to be your first term, whatever you got. So this is going to be a half divided by a half. All right. All right, good enough. This is going to be 1 times 1 minus a half squared over 1 minus a half. It's just always going to be doubling the number overall. So this could be 1 minus a quarter is going to be 3/4 over a half. So then it's just going to multiply the top and bottom by 2, so it gets us to be 3/2. 7/4, this is going to be 1 minus 1/8. 7/8 divided by half. It's going to be twice 7/8, which is 7/4. Good. All right, so all that's going to work. What we're mainly concerned with then is this thing. So like, how does this n work? This appears to, this n. It appears to need power of 2 in for n in order to make this actually work, right? So for n being 1, 2, 4, 8, 16, 32, and 64, what are we then going to be able to get for log base 2 of n? This is just going to count up. So what exponent on 2 is going to get me? 1. Okay, that's an exponent of 0. Yeah, what exponent on 2 is going to give me 2? That's 1. What exponent on 2 is going to get me 4? It's 2, 3, 4, 5, 6. So this is going to be partial sums with log base 2 of n. So 0 to 0 is just going to get you 1. 0 to 1 is going to get us 1 plus a half, which is going to be 3/2. Okay. So it seems to be working so far. 0 to 2 is going to get us 3 numbers, 1, a half, and a fourth, so it's going to be 7/4. Okay, good. Good, good, good. This is going to be 15/8. And a 16th. It's going to make it 31/16. Plus the 32nd is going to be 62/63. 30 seconds. Plus the 64th is going to be 127. 2 to the n minus 1. Right, so this is your so n times partial sum log base 2 of n. It's going to get you your Mersenne primes. Right, with the exception of 1. 3, 7, 15. That's not a prime. Oops. Right, it's existence, not uniqueness. Go for it, Bertram. I think you need to rephrase your question. I know what you're talking about, but... So what is it that you're talking about in terms of what of natural log gets you 1 over x? Now, I know you're going for derivatives, but... So, what you're wanting... So what you're doing is you're saying that you're taking the derivative of a particular thing, which again in this case is the natural log of x. Okay, and in taking the derivative of the natural log function, this is going to get you 1 over x. Times the derivative of whatever variable you've got. So here, this is saying, well, let's let, this is like super advanced for you. Let 2x plus 1 just be u for a moment. Not u, but you know what I mean. So here, we're taking the derivative of the natural log of u, which is going to be equal to 1 over u times the derivative of u. And here, if we take the derivative of u, we get 2. Nope, not enough room. 2 dx. So then we can back substitute and say I want 1 over u is going to be 1 over 2x plus 1 times du is now 2 dx. So this is what's called a generic derivative operator. So it just takes the derivative of everything that's there. You still have to follow all the other rules, if there are any other rules you know. but anything that's a variable in the entire area that you've got, you're going to be taking the derivative of it at some point. I prefer the generic derivative operator because it kind of lends itself to just saying, like, here's how the chain rule works. Here's how all this other stuff works. Right? We allowed ourselves to say, let's just let this stuff on the inside of this function just be a different variable for a minute. So we trade it off. We let it be u. We want to take the derivative of the natural log of u. It's 1 over u du. 1 over u du. Alright, then to find du, this is to figure out what the relationship is between x and u, and therefore dx and du. So in this particular case, dx is half the size of du. Had to think about it for a minute. Or du is twice as large as dx. That's a better way to think about it. And so we use that particular scaling factor to our benefit. What do you think? If you want to see something else that's wild. Another way to do it is you say, okay, I want to take the derivative of natural log of 2 times, well, yeah, that's okay. 2 times parentheses x plus a half. That's the same as taking the derivative of the natural log of 2 plus the natural log of x plus a half. So if we take this derivative, so that is a natural log, yeah. Right, the antiderivative of 1 over x dx is a natural log of x plus c, not, as one might think, not x to the 0 plus c. Right, it breaks the power rule, having this -1 exponent. It's one of the weirdest things, but it works. So we take the derivative of the natural log of 2 plus the derivative of the natural log of x plus a half. Again, this is another wild thing that happens. The derivative of the natural log of 2 is 0 because it's a constant. So the way that the logs work is that any of these constants that are multiplied on can just get shipped out, right? They're not actually used at all. The derivative of the natural log of this thing is going to end up being 1 over x plus a half. Right, and there's nothing else attached to it. Because here we've just got, if you wanted to, again, go the u du route, do u substitution, you say that, okay, x plus a half is going to be u, so then take the derivative of both sides, and dx is du. It doesn't really help you. It doesn't change anything. So the derivative of all this stuff ends up being this thing. Again, that is dx. Multiplied by dx. Okay, but then we can also say, all right, the derivative operator, that's operating on all this stuff. Natural log of 2 parentheses x plus a half is going to be equal to then 1 over x plus a half. Notice that I moved the dx from this side to the other, divide by. Alright, so we get our generic operator, capital D, then becomes the specific operator, which only operates on x. Alright, so the ordinary differential operator operates on x. Well, not quite. So you do the u substitution thing again. Where if we did 1 over 2x plus 1 dx, then we would look at this and say, okay, we're doing a u substitution again. So this is going to be 1 over u, but then we have to figure out what the relationship between dx and du is. So if u is equal to 2x plus 1, then du is equal to 2 dx again. Right? No surprise here. It's the same stuff as we had before. Okay, but then we need a 2 dx. We don't have a 2 dx here. So make a 2 dx by balancing it. It's going to give you a half to the front. Du. Now, you may see some people who will take a look at this here, and say, this means I can do du times a half is equal to dx. And whereas that works okay for constants, do not ever do that for variables. So I have seen some cases where somebody said, okay, u is equal to 2x squared plus 4x, and therefore plus 4. And therefore du is equal to 4x dx. And their integral was like, 3 over 2x squared plus 4 dx. And they're like, but I don't have a 4x. Like, I don't have an extra x. So I'm just going to take that whole thing over and say that du over 4x is equal to dx. And now I can just trade out dx. Do not ever do this. Ever. It's not even necessarily a divide by zero error, right? Because you could be evaluating it somewhere way over there, okay? But you can't do this because here you don't have an x. You don't have an x to spare. It just doesn't exist. Right? It needs to be here. And it's not. And you can't go, okay, x over x and pull 1 in. No, you can't do that. So this whole thing is just garbage. In my world, what? Hashtag not sponsored. My spouse got me some of these Ghirardelli ones. Happy Valentine's Day, everybody. May the martyr of Saint Valentine go ever sweetened, I guess. I'm sure he'd be horrified. Hey, being single on Valentine's Day is good. After all, tomorrow is Happy Sweetly or Steeply Discounted Candy Day. It'll all be in the dollar bin. At least here in the U.S. Oh, you European types have way better candy. That's why all of ours is imported. Ayo. All right. I need to make a note to myself to show this to my students when my Calc 1 people get up to that level. Yeesh. So we actually have a Lindt chocolate factory in Stratham, New Hampshire, which was a couple towns over from where I lived growing up. So that was always very interesting. And then the next town over, Portsmouth, had a seconds shop. So like all of the candy that got screwed up somehow went to the seconds shop. And it was steeply discounted. So we grew up, you know, pretty close to the Lindt candy factory. That was pretty good. That particular chocolate obviously was not imported, but it was certainly not quite the same as, like, you know, Hershey, which, as ubiquitous as it is, and as much as I ate growing up, it's you know, over-sugared and under-flavored, quite frankly. We import Ghirardelli, we import, we might actually have a Ghirardelli in the States now. I wouldn't be surprised. And same with Cadbury. But I'm pretty sure that at the very least some of those are imported. A lot of our friends and neighbors import from whatever their home country is. So if they have moved to the US at any point in their life, oftentimes they still have ties back in, you know, well, even if this might be their home country, but their family's home country. So we get some really good, this isn't like, you know, countrywide or anything, but Yeah, some of our... Yes, yes he does. Unless you didn't mean it badly, in which case, well... No, brain. Throw me the brain. Come on. Built off the backs of his workers. Yeah, it's really scary when you start... It's really scary when you start looking at all the times he was doing union busting and all of the, like, millions of dollars spent union busting instead of just paying his workers more. I guess, like, he didn't want him to get too many steps up the ladder or something. I don't know. Whatever. I don't know. I would like people to contrast, like, any company in the United States, I don't care what it is, with Dumula's Market Basket. Now, they are a... Yes, just like all the conservatives around. So the Dumula's family was like really big in New Hampshire and Maine and Massachusetts. Still is, really. Artie Dumula was this guy who, his whole extended family is French Canadian. Obviously, you know, de Moula. Wonder what that's supposed to mean in French. But yeah, so his extended family is all like French Canadian, so no surprise. There's like a huge French Canadian contingent in New Hampshire, especially people who are like, you know, 5 generations deep and have no idea that their name is not pronounced the way they pronounce it. I mean, let me be fair, it's pronounced however they want to pronounce it, but you know, over the centuries or whatever. So I mean, it's how a lot... There is... God, what was their name? I'm trying to remember. There were like 10 people at my high school who all had the same last name. They're all like, you know, 5th cousins or something like that to each other. A couple of them are actually closely related, but... Oh. Here, let's write this one down. We don't have any like actual French Canadian people in New Hampshire. No, seriously, my barber was actually French Canadian, and like 3 of my French teachers were French Canadian. Yeah, so this is a very common name in New Hampshire. It is in French, Pelletier, which in New Hampshire speak is Pelletier. Oh, you dumb Americans pronouncing your name wrong. So yeah, my it's not English, it's because if you go to England and ask them to pronounce it, that's also going to be sounding different. Pelletier. But yeah, you can very occasionally, you might actually catch something of an accent in my voice. I mean, it's American, right? But something that deviates from the American standard. It's very subtle, and occasionally you'll hear it, but it's very New England. So American standard is usually like both coasts and more metropolitan areas in the rest of the country. um, you know, obviously not Texas, but that wasn't a good Texas accent. That almost slipped into like Bahaba up in Downeast Maine. Yeah. I'm gonna have to do a stream at some point reading Bert and I. No, okay. That's not it. Oh my god. That's too great. Sorry, I'm being terribly rude. Yeah, so there's these two guys who are named Marshall Dodge and Robert Bryan, and I believe it was Marshall Dodge at Yale decided that he was going to study like it's kind of a hobby. He was going to study. Okay, both of them. Marshall Dodge and Robert Bryan at Yale in the late 1950s were deciding that they were going to study the anthropological storytelling of the people of Downeast Maine, which Downeast is this place in and around Bar Harbor. Map. Yeah, so way up here. Right, way up here, down east in Acadia. This, like all of, oh no, all of this part, that is entirely Canadian, Canada. Aroostook County, all the way up here, in most of, let's see, this is all coastline. I can't remember if this is just a river right in here, but either way. So down east is a very specific accent, and it has a very specific sound to it. And so Marshall Dodge and Robert Bryan, who were going to school in Yale, decided that they were going to study the storytelling methods of people in Down East. And so they went up there and they started talking to people and trying to get a sense of like how they talked and stuff like that. And then they started writing scripts about the various storytelling methods and stuff like that. There was like comedic scripts. And so then they would start performing around Yale, and at some point somebody was like, you've got to record this. And so the two of them eventually made a series of stories called Bert and I, or Bert and I, which were an homage to the storytelling methods of the Down East people. And so they came up with, 100 some odd stories that are on a whole bunch of CDs now, tapes, records, way back when. And yeah, I think I want to... It was an interesting moment, probably a couple hours ago, when I realized the connection between me sitting rapt listening to people perform Bert and I like 35 years ago, and me listening to Sunil Singh talking about, trying to make mathematics more of a storytelling experience. And I went, oh, that's where it came from. Listening to my dad tell stories, listening to the guys doing Bert and I, listening to my grandparents talk, even though I thought I was bored. Like, no, it all makes sense now. It's all just part of one big amalgamation of everything. So, I think I'm gonna have to find the scripts for Bert and I somewhere and end up performing it for you all. Probably a bonus stream, not Tuesday, Friday, but anyway, what do we got? Anybody want anything else? So that's 2 raised to the nth power minus 1. 2n minus 1 is like a bunch of odd numbers. Now these are odd numbers, but they are specifically 2 raised to the n minus 1. So 2 to the first minus 1 is 1. 2 to the second is 4, minus 1 is 3. 2 to the fourth, there we go. That's wrong. Hang on. This number? No, it's this number. 2 to the n. Huh. I was using these before. How'd I screw up? It's not that n. This is just 1, 2, 3, 4, 5, 6, 7. Okay, yeah. So 2 to the k minus 1 is really what we're going for. Second here. Alrighty. Let's see. What I do with my students today in Calc 2. Yeah. This was it. This is all I gave them. So there are 4 pens labeled A, B, C, and D in which cows are put. That is the only piece of information I gave them. You've got cow fields, A, B, C, and D, into which cows are put. The numbers 1 through 9 will be used at most once. Can you find the values for A, B, C, D, and W, X, Y, and Z? So there's an obvious question that comes first. Okay, specific question that comes first. Yep. Doing this on like a 10-second delay, it's fine. Yep, well, like I said, each number 1 through 9 is used at most once. the numbers are put into A, B, C, D, and W, X, Y, Z. Let A equal 1. Good start. Okay, why? No, B. Okay, so I will tell you that if you go 1, 2, 3, 4, 5, 6, 7, 8, 7, in alphabetical order, this will be incorrect. Now, like I said, there is a, reasonable question that is, or should be jumping out at you. If you just rotate A, B, C, and D, yeah, it's still going to be wrong. There is no arrangement here of A, B, C, D with those values that is going to match up with the solution. We're not going to sit through all of the different, possible permutations of everything else. Right, so really, the biggest question is, what do W, X, Y, and Z represent? And that's one of those things that they weren't, Sunil suggested, don't tell them. Give unhelpful hints like, well, what do you think it represents? So if they're gates, right, then you have a problem because the cows won't necessarily stay in fields, and then therefore the numbers at some point might be equal between them, and that's just not going to work. Can't have equal numbers because, again, all of the numbers can only be used at most once. Data Basics. Good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We do a lot of things mathematical in this space, so if you're at all interested in talking about some math, let me know. And if not, you're welcome to hang out, do whatever. We're just talking about a logic puzzle that I gave to my Calc 2 students today. All of the groups but one got it fairly quickly, and the last group I kind of nudged them along until I said, all right, well, why don't you all work on it, think about it for a little bit. So hopefully they'll come back on Thursday and be like, ugh. Sure. Ah, interesting. So if they were sums, we'd have, for instance, a 3, a 6, 7, and a 4 in these particular places. Now, obviously that doesn't work, but we were expecting that that was not going to work for, you know, just the same stuff. Because again, we got a duplicate of 3 and a duplicate of 4. But this does take care of 7 and 6. Yes. Well, rotating everything is useless. You were just saying rotate A, B, C, and D all by themselves, and then W, X, Y, Z would have stayed where they were. So the main problem that we had was that W, X, Y, Z are, like, they mean something. You just have to figure out what they mean. So if it is sums, right, does it make it any better? Are you able to figure something out logically based on that? So if these 4 things are sums, you know immediately that the lowest value the sum could have is going to be 3. And then we could also have a high value of, 1 and 8 gets us our 9. So, yeah. So that also means that 9 itself has to be 9 itself has to be in the sums. It can't be in any of the squares. Are the cows spherical? Probably. You do have to assume that. And they have to be in a vacuum. So your 1 and your 2 have to be numbers of cows in the fields in some arrangement. And there's only 2 places where it's going to be non-symmetric, right? So it's either going to be next to or diagonal from. So if we erase these, say, okay, we could have a 2 here, we could have a 2 here. And again, those are the only possible symmetric, like non-symmetric ways to do this, because if we put a 2 over here, that's just the same as anything else. And again, we could rotate and flip and do all sorts of other stuff. Okay, so 8 could be here, and again, either one of these, I guess. if 8 is here, that means that 2 is here, and then 8 and 2 is going to be a problem. Yep. Right. So 8 can only be paired with 1. It can't be paired with anything else. So that also means that 8 has to be a sum. Yeah, I do too. Works out really nicely. So I've got a late start pre-calculus class that is actually going to run. Thank goodness. I was getting nervous. Because I don't have full load yet. So it was going to be a little hectic. The dean was like, hey, look, you know, at this point you have to run this class because you know we don't have time to just mess around. Don't really have time to just wait and see what happens. Alright, so 9 cannot be a sum with 1, because then again, if it was 9 here, this would be 8 here, which we already said 8 has to be in the sums. So 9 can't be here. Or here. Yeah, symmetric again. So 9 has to be in one of these lower two. And again, for simplicity's sake, we can always just say, alright, look, it's going to be this way. Pre-rolls. So we said that 9 can't be attached to 1. Sorry, no, you stepped away. Because if 9 is attached to 1, then it has to be 8 that's matched up with it, but we said 8 has to be a sum, because again, there's nothing else it could be connected to. there's nothing that 8 could be connected to that's less than 9. So 9 has to be in the sums. I guess it could be the case that 9 is just not used, potentially. So we could also take that away, I guess. Okay, why? Are there any other options? Can we do 6 and 3? 5 and 4? Mm-hmm. So like 7-2, 6-3, 5-4. Why not? Okay, so if we did 6-3 like that, then this would be 7. And we could use a could, right? Can't use 2. Well, hang on. 2, if used, must be in a field. So can we skip 2 altogether, is really the question. So if we just skip 2, because again, there's one number that's not going to be in there. So to be skip 2, we got 3, we need 4 and 5. So if this is 4 and this is 5, this would be 7. Right? And now that's double 7. Yep. Right, 5 would make this a 6, so that's not going to work either. So then it would have to be a 2, but then this is a 3, so therefore this can't be here. But, again, if we back it up, so 6 and 3 is out. Now you wanted to go for 7 and 2. This one's 8. Alright, so then what do we put here? So we've got options. Again, we've already got 2. And this is going to be 3 or 4 or 5. Can't be 6 because again this is a 1, so it's already taken. 3 in the top right corner. Alright, so if this is 3, then this is 4 and this is 5. And we take 6 out. Yeah, so I told my students that they were going to have to figure out what it was, and they were like, well, do we need to get the answer, like the whole thing figured out? And I'm like, well, the goal as I had stated originally, was what number's missing. So realistically, if you figured out what number's missing, you have figured out the solution for everything. So, yep, awesome. So I was like, you know, you can. Some of the students were starting to think about this in terms of algebra, and so they were like, well, this means that like a plus b equals x, and b plus d equals y, c plus d equals z, and I'm like, really? A plus c equals w. Right, because now we've got a lot of known values, but a lot of unknowns, and not enough equations to make it work. So, you know, it's 4 equations for 8 unknowns. So you'd have to figure out, like, how this all worked. Now, there are some other, like, hidden equations in that these numbers can't be the same. So there's some connection. We just don't know what it is right offhand. So the let me know if I'm answering this correctly, but so each number 1 through 9 is used at most once, and so there are 8 locations where you can put numbers. And so the question really was, what number's missing? If you know what number is missing, then presumably you have actually solved the entire problem. Some other students, I think, had 3 was the missing number, and I don't know if that was a different save state or a different solve state, or just they messed up. I thought it was unique, but yeah, maybe I just wasn't looking carefully enough, and they had a duplicate number somewhere, or numbers that didn't add up to the right number. Also true, yeah. So I know that 4, 5 cannot be true because 1 and 4 is going to make 5 here, so that would collapse. All right, if we went 5 here, 4 there, this would end up with 6 up there. And so we've got 1, 4, 5, 6, and 9. We have 2 and 3 and 7 and 8. Can't be 2 because then this would be a 6. We'd have a duplicate. If it were 3, then we'd have a 4 here, but we already used 4 down there, so that can't be a 3. 7 here would make this an, I'm sorry, 7 here would make this an 8. And 7 and 4 makes, yeah, and plus 4 is going to make these go over. Right. So 5 and 4 don't work at all. Need 2 to be a lower number. Is there a solution without 1? Also a good question. So we could try. So if we assume that 2 is going to be the lowest value, that means that we can plug 2 into any of these particular fields. Just let that be our initial state. So assume that 2 is going to be the lowest number, and we are not going to include 1. Yes, so the rectangles are intended to be the sum of the 2 pens that are connected to them. Okay, so with a 2 being the lowest number, the 8 and the 9, again, we can't do anything with it, and in fact 7, if it's attached to, only has one other number, only has one number it can be matched with, which is 2. So 7 is also going to have to be a sum if it's, well, it has to be used in this case. Right, 8, 9, and 7 all have to be used. And as sums. Which means either 7's going to be here or a 7's going to be here. Right, again, without loss of generality, we can swap those for the other 2 if we feel like it. So either this is a 5 or an unknown. We don't know what that's going to be. Right? So if it's 7. What's the highest value it could be? So that'd be if we have a 6. Let's assume we have a 6 here. That's going to make an 8. And then this is going to have to be a 3 in order to make this a 9. Right? Any higher it's above 10, so we can't do that. Alright, so then we need another number here. 4. It's going to make 6, so that's not going to work. Right? Right, 5 is going to make an 8, 6 is going to make a 9. Yep, doesn't work. Landon, sure. A harmonic oscillator is something like a pendulum or a plate that is being affected by sound waves, or any number of things, really. So what we're going to have is, excuse the horrible drawing, but what we're going to have is something that is going to have a periodic some sort of periodic repetition. And it doesn't have to be something that remains in a steady state. So this would be steady if it's going to remain with the same pattern. We also have damped, where the oscillations will decrease over time. Now this is something that you're probably used to. Right, if you have a pendulum and you just let it go, if the clock is not actually working at that exact moment in time, it will just swing back and forth and then get lower and lower and lower and lower and lower, and eventually the inner workings of the clock is going to cause it to swing to its lowest point and stop. So we end up with something that looks like this. So we still have the same period. Yes. Yeah, Professor Lewin did a pretty fun experiment, which is kind of typical. He put his face against the wall, or back of his head against the wall, lifted the bowling ball that was attached to his ceiling anchor directly onto his nose, and then let go. It swung all the way across the lecture hall and then all the way back, and didn't even make it like to within a few inches of his face. Like, never even close. I'll call the Navy, I guess. Ayo. Yeah, if there's like a breeze or something like that, that is an outside force, and it could put energy into the system, and it would smash his face on the wall. So that's something you don't want to do. There were also many experiments done by other scientists who do the same sort of thing. So it he found it. Yep. That's the one. Right, and right around the 1 minute mark, he puts that to the test, where he picks up the bowling ball, walks over to a plate of glass that he's set up on like a little stand, and he does throw the bowling ball. And by doing that, it puts too much energy into the system, and it swings back and smashes the glass everywhere. And he says, all right, so what happened? Discuss what happened. And he goes, okay, now I'm going to put myself on the line, and puts his face on there. And like I said, it missed him by a good couple inches. It's like, okay, see? Air resistance is a thing. So a damped oscillator ends up having decreased oscillations over time. Note that the period will always be the same. So it will reach its period, its maximum, at like exactly... Yeah, probably still flinches, but he also plays it up for show. So the period is always going to be very, if it's not exactly the same, it is very, 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 very close. And this ends up, yeah, doing this. And then there's also this thing called overdamped, which goes like this. And for this, if you would think about, for instance, a spring, like a spring mass system, that normally you you lift up the weight, you drop it, and the spring causes the thing to go up and down in the air. It is a harmonic oscillator, or damped harmonic oscillator, but it's so minute that it almost looks like it's in a steady state, right? Where the oscillations are so close to exactly the same number from one period to the next, to the next, to the next, that you'd think it was a steady state system, but it's not. Right? Now imagine, instead of dropping it and then it goes out to its like maximum and then again comes back up and goes back down and comes back up, instead of doing that in air, imagine what would happen if you dropped it in honey. So here, or if the whole thing was in honey in the first place, right? So if you've got this spring that's stretched out really far and then you let it go, it might still like go out to a maximum length, out to a maximum length and then start coming back, but it might, for instance, slow down really quickly because in honey, for example, the system itself is over damped. It can't actually compensate for the resistance of the fluid that it's in. In the case of the damped one, right, it's decreasing over time, but it's because of a negligent force. Something like, not negligent, negligible, a almost negligible force like air resistance. The friction that is causing energy to dissipate out of the system due to heat. Like, it's just so small that the damped system almost looks steady. But when you've got something like honey, then you've got an overdamped system, and then you can't even get like a good swing out of it, if you will. It's just going to end up stopping the motion too quickly. And it doesn't even have to be this. There's all sorts of overdamped. So, yeah, it can go up one and then just start coming back down like that. Or you could pull it to a particular area and then it just drops down. So like, this would be like a spring mass in honey. All right. Anybody have anything else? Been going for about 2.5. Oh yeah, that's a fun one. So the state for the individual problems ends up being you've got a y double prime plus a gamma y prime plus a, man, I forget what it is. There's some sort of constant here. So just c times y is equal to 0. So this right here is going to be your spring force acceleration. So that's our damping constant. Well, it's just really kind of a fundamental it's kind of a fundamental type of problem. So it doesn't necessarily even matter whether or not you're going to do this in real life. Flamelin, you know for a fact that everybody says that. It's a typical, stereotypical question at this point. The student's going to say, when am I ever going to use this? Well, it doesn't really matter.